All right, so today the first thing that we're going to talk about is the maximum average power transfer. So hopefully we all recall from circuits 1 that if we're able to express a DC circuit, so I'm just going to put this as VThev as a DC quantity, and the resistance RThev, and we connect some load impedance across the terminals of our Thevenin equivalent circuit, where this will be our voltage VL, and this will be our current IL. We learned that maximum power transfer occurs when that load resistance RL is equal to the Thevenin resistance of the original circuit. You guys vaguely remember that? Okay. So in order to get that result, what we did was we effectively maximized our power relationship, right? So the power absorbed by our load resistor, nothing more than the product of the voltage drop across the load times the current flowing through the load. And if memory serves me correctly, this came out to be V Thevenin squared times RL divided by R Thev plus RL squared. So we maximize that relationship to get this one. I'm bringing this relationship up because we're going to see it again in a few minutes when we're looking at our AC circuit version of maximum power transfer. So let's say that we have now an AC circuit that we can reduce down to its Thevenin equivalent circuit, which would be some phasor voltage VThev in series with some impedance. Let me move this up here. Let's call it ZThev. And we connect to our Thevenin equivalent circuit now some load impedance, ZL, like so. Where this is the voltage drop across our load impedance, and this is the current flowing through our load impedance. Okay. So in class Wednesday, and also back in circuits 1, we learned that the average power was Vm Im cosine theta v minus theta I, right? So what does Vm in that expression represent? It's the magnitude of the voltage drop across our element of interest. So that would just be the magnitude of phasor voltage VL. Similarly, Im would be the magnitude of the phasor current IL. And cosine theta V minus theta I would be the angle of really just the impedance. So what we are going to do is effectively we are going to use complex number relationships to effectively solve for the magnitude of our voltage VL in terms of our Thevenin voltage and Thevenin impedance. We're going to solve for the magnitude of the current IL in terms of our Thevenin voltage and Thevenin impedance. And we're going to solve for cosine theta ZL in terms of our Thevenin voltage and our Thevenin impedance and all of that kind of good stuff and see what shakes out of that. So let's look at the voltage drop across our load impedance first, okay? So I would argue that we could very easily use voltage division to find this voltage VL, right? So that would be our phasor Thevenin voltage times the impedance ZL divided by Z Thev plus ZL. Direct application of voltage division, nothing remotely wild or crazy there, okay? So what I'm going to do now is I'm going to express my impedances in rectangular form, okay? So that's going to look like V Thev in the numerator times a factor of RL plus JXL. So I just decomposed my impedance into its real and imaginary parts, divided by R Thev plus RL plus J X Thev plus XL, right? Where I'm just adding the real parts of my impedances together in the denominator and adding the imaginary parts of my impedances together also in the denominator. So are we all okay with this? Okay. So the magnitude of the voltage VL will actually be nothing more than the magnitude of each constituent part of this. So we would have the magnitude of V Thev multiplied by the magnitude of RL plus JXL, which is literally just the square root of RL squared plus XL squared divided by the magnitude of the denominator, which is going to be the square root of R Thev plus RL squared plus X Thev plus XL squared. And all of this is under a square root. So because we're dealing with magnitudes, there is no imaginary parts, right? We're just dealing with a length of a vector. Okay. So now we're going to do effectively the exact same thing for the current. So we could find our current IL literally by just using Ohm's law here, right? So that's just going to be V Thev over Z Thev plus ZL. And we're going to break this down into, or these impedances down into their real and imaginary parts like we did just a moment ago. So we'll have V Thev divided by R thev plus RL plus J X thev plus XL. And then doing the exact same thing to find our magnitude. We would have the magnitude of V thev all over the square root of R thev plus RL quantity squared plus X thev plus XL quantity squared. So we figured out this part and this part. So now we just have this last little bit of figuring out what the cosine of theta ZL is in terms of parameters that we know. So what I'm going to do is I'm going to make a plot here. And I'm making an assumption just for illustrative purposes that this impedance plotted on a complex plane is going to be in the first quadrant, but the relationship that we're going to derive is equally valid for anywhere. I'm just drawing it in that particular way, right? So here's my imaginary axis. Here's my real axis. And so I can just say, generically speaking, that my impedance ZL might look something like this, where the projection of ZL onto the real axis is RL, and the projection of ZL onto the imaginary axis is XL, and the angle formed between my vector ZL and the positive real axis is my angle theta ZL. So I'm going to call this 8th grade trig because I don't know what year you guys took trig. But all we're going to do is just a very, very simple trig identity here, right? So going back to whatever high school math classes you took, what's the fundamental definition of a cosine function? You guys remember SOHCAHTOA? Let's use that, right? So sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. So what's the adjacent here? The adjacent would be RL. The opposite would be XL, right? So cosine of theta ZL is going to be RL in the numerator because that's the adjacent. What's the length of my hypotenuse? Square root of RL squared plus XL squared, just from good old Pythagorean theorem. Anybody have a problem with this? It's literally simple trig. So we have all three constituent parts now, so we're going to put those together, okay? So we could say that our average power is going to be the magnitude of our Thevenin voltage times the square root of RL squared plus XL squared divided by the square root of R thev plus RL squared plus X thev plus XL squared. So this part right here is just the magnitude of our voltage, magnitude of our current, we're gonna have the magnitude of V thev divided by that exact same denominator, R thev plus RL quantity squared, X thev plus XL quantity squared. And then lastly, we have our cosine relationship, which is just RL over the square root of RL squared plus XL squared. So I believe that we can see very obviously that we have a common factor of square root of RL squared plus XL squared in the numerator and the denominator. So those guys cancel each other out. We can also notice that the denominator in the voltage part and the denominator in the current part are the same thing. So that square root is going to effectively go away. And that's going to leave us with the magnitude of the Thevenin voltage squared times RL divided by R Thev plus RL squared plus X Thev plus XL squared. All right. So this is a kind of an odd question, but I can't really think of a better way to phrase it. What effect is reactance having on our average power according to this equation? It's decreasing our average power, right? So we're seeing some quantity in the denominator. So as the denominator gets larger, our overall power gets smaller. Absolutely correct. So if we want maximum average power transfer to occur, then that means we need to make our reactance effectively zero, because any reactance, whether it's positive or negative, is going to decrease the amount of average power absorbed in our system. So our first constraint is that XL needs to equal negative X thev in order for maximum average power transfer to occur. Okay. So this cancels out all our reactance and we're only left with resistance. Okay. So we can now say that when XL is equal to negative X thev, the average will be equal to the magnitude of V thev squared times RL divided by R thev plus RL quantity squared. Does that relationship look familiar? It should. I wrote it down pretty much exactly when we were looking at our DC circuit. It's the exact same thing, except we have the magnitude of a Thevenin voltage instead of a DC Thevenin voltage. Literally everything else is the same. So from this equation, because we already dealt with it in circuits 1, we could say that for maximum average power transfer to occur, we need RL to be equal to positive R thev, right? And combining these two results tells us that maximum average power transfer in AC circuits occurs when RL, or excuse me, ZL is equal to R thev minus J X thev. What is R thev minus J X thev? So what's R thev plus J X thev? That's what we called Z thev earlier. When we change the sign on the imaginary part, what's that called? Complex conjugate. So this is nothing more than the complex conjugate of the Thevenin impedance of the system. So Z Thev conjugate. This gives us a P-max relationship that is actually 1/8 the magnitude of V Thev squared divided by R Thev. Just to be clear here, when we had a DC circuit, it was 1/4. Because we have an AC circuit, we have that damn pesky factor of 1/2 that keeps cropping up in all of our relationships. So that's why we have a factor of 1/8 here. All right, so that is maximum average power transfer for AC circuits, incredibly similar to maximum power transfer for DC circuits. Okay. All righty. Any questions about this bit before we go on about our day? Yes, sir. Oh, sorry, it's the magnitude of the phasor Thevenin voltage. Thank you, I forgot to put the bar over it to let you know that, so I appreciate it. Any other questions? All right. So now let's talk about effective values. So because we've had circuits one, we have all been exposed to effective values before. So how in detail do you guys want me to do this derivation, or do you want me to just remind you of what the equations are? Okay. All right, so the effective value for a periodic voltage signal is nothing more than the square root of 1 over the time domain signals period times the integral over exactly 1 period. Here I'm putting the limits of integration to be from 0 to t, but they could just as easily be from negative capital T over 2 to positive capital T over 2. Does not matter as long as we're just integrating over 1 period of the square of our voltage waveform with respect to time. And the units of our effective voltage will be expressed in volts RMS. We use that RMS designation to let people know we're dealing with effective values. Okay? For a current, it's literally the exact same derivation, right? So here we'll just have the current waveform squared instead of a voltage waveform. And so our units should be in amps RMS. Um, so for a sinusoidally varying signal, so if we had, say, V of t was equal to Vm cosine omega t plus some arbitrary phase angle theta v, or I of t were expressed as Im cosine omega t plus some arbitrary phase angle theta I. Again, we learned this relationship in circuits 1, so that's why I'm not deriving it. Our effective value would simply be Vm over the square root of 2. And the effective value for our current waveform would be Im over the square root of 2. Okay. Hopefully, again, this is all review here. So where we're going to introduce something new here. Actually, let me ask you guys a question. So in the homework set associated with this material, I give you guys some graphical representation of waveforms. Okay. And I ask you to determine their effective value. Do you guys want to work an example of that, or are you good applying this equation because you've had to do it before? Work an example. Okay. So let's say that I have following waveform. Let's arbitrarily call it a voltage. And my waveform looks something like this. So it is linearly increasing for some amount of time, and I'll define that in a moment. And then it stays constant for some amount of time, and then immediately drops back down to 0. And then that cycle just repeats over and over and over again. So let's say that this is t is equal to 2 seconds. Over here is 0. This point right here is t is equal to 5 seconds. And the maximum amplitude of this thing is 10 volts. So if we wanted to find the effective value of this odd voltage waveform here, we would simply apply our equation, right? So V effective, generically speaking, will be 1 over the period times the integral over 1 period of our voltage waveform squared with respect to time. So let's start working on things here. What is the period of this signal? 5 seconds. Nothing particularly difficult about pulling that straight from the graph. I'm going to choose to express this voltage waveform as a piecewise function. And so that means that I'm going to need to split my integral into multiple intervals in order to accommodate that, right? So we can see very easily that our function behaves in one way over the interval from 0 to 2 seconds, and then we'll fill in some stuff there in a moment. And then it behaves in a different way from 2 seconds to 5 seconds. So let's come back up here and let's figure out how to express this voltage waveform as a function of time. So let's start with the 2 is less than t is less than 5 interval, because that one's really, really easy. So what's the voltage doing over that interval? It's a constant 10 volts as far as I can tell, right? So we're just going to throw 10 volts right there. Nothing remotely difficult about that. And then in our equation down here, we are going to have 10 volts squared dt. We got to remember to square our voltage waveform. So what is the voltage signal doing over the interval from 0 to 2 seconds? It's a linear increase, absolutely. So we can put it in y is equal to mx plus b format, right? Slope intercept, you may have heard it called that or whatever. So what's the slope of this thing? 5 what? Volts per second. What is the intercept or the y-intercept? 0. So we can just leave it as 5 volts per second times time, okay? So over here, I'm gonna have, when I square this, 25 volts squared per second squared times t squared dt. Because it's right. So the value of the voltage depends on what time we're at. Whereas from 2 seconds to 5 seconds, the value of the voltage is literally just 10 volts everywhere in that period, right? So at t is equal to 0, our voltage is 0. At t is equal to 2 seconds, our voltage is 10 volts. And then everywhere in between, it's just linearly increasing. Yep. All right. So what I'm going to do now is I'm just going to kind of distribute some things, okay? So I have this 1 over 5 seconds. I can pull that 25 volts squared per second squared out of that first integral because that's a constant term. And then I'm going to integrate t squared. What's the integral of t squared? T cubed over 3, right? And this will be evaluated at 2 seconds and 0 seconds. And then I have a 10 volts squared, that's a constant, so I can pull that out. So I'm just going to call that 100 volts squared. Now I have the integral of dt. What's the integral of dt? T. Evaluated at 5 seconds and 2 seconds. Close that bracket there. Make the square root sign go over the whole kit and caboodle. All right, so I've got this 25 volts squared over second squared. So let's see. t cubed over 3 evaluated at t is equal to 2 seconds gives me 8 seconds cubed over 3. So that's 8/3 of a second cubed, or times second cubed, minus 0. Plus 100 volts squared. And so now I'm going to have 5 minus 2 seconds is just 3 seconds. And keeping on here. So 25 times 8 is 200 volts squared divided by 3 seconds. My units work out okay there? So seconds cubed divided by seconds squared. Oh, no, that should be a second in the numerator. My apologies. So 200 over 3 volts squared seconds plus 300 volts squared seconds. And now seconds in the numerator up here cancels the seconds in my period down here. And I'm left with, let's see, so 300, square root of 1100 over 15 volts squared. If I did my mental math right, please tell me if I did it wrong. It's always suspicious when I'm doing math with numbers. I called that 300 as 900 over 3, 900 over 3 plus 200 over 3 seems like 1100 over 3, and then I multiplied that by 1 over 5, which is where that 15 came from. So I think that's correct. And then throw this in a calculator. Square root of 1100 over 15 is 8.563 volts RMS. All right, we did an example and killed 10 minutes. All right. So the last thing that I want to talk to you guys about for today is what an effective value looks like in a multi-frequency circuit, okay? So when we looked at the instantaneous power in a multi-frequency circuit, we had something that looked like this. Let me do this here. Or a multi-frequency signal, let's put it that way. And I'm not going to formally derive things because we should have enough of an understanding as to how things work to not have to suffer through on the math. Okay. So as I was mentioning a moment ago, in a multi-frequency circuit, we saw that our power was of the form where we had some DC term, and then I'm going to say plus P at twice omega 1, or that's just the 1/2 VM1 IM1 squared bit times cosine of twice omega 1t plus dot dot, where that's just the Fangs angle stuff. It's not remotely important with what we're looking at. And then we had a twice omega 2 term times cosine of twice omega 2t plus our phase angle stuff. And continuing on down here, we had a power at a omega 1 minus omega 2 frequency, cosine omega 1 minus omega 2t plus our phase angle stuff. And then we also had a fifth frequency at omega 1 plus omega 2, cosine omega 1 plus omega 2t plus dot dot. Okay. The reason why I'm bringing this up is because our effective value is in some way related to our instantaneous power. And if we had derived that, we kind of would have seen, okay? So if we had a voltage signal that was a multi-frequency voltage signal and we squared it, it would wind up looking something like this instantaneous power expression, but instead of these PDC terms, we would have voltage squared out in front, right? So we have this DC term right here. We have this twice omega t term right here. We have this twice omega 2 term right here. And then we have these cross-frequency terms, right? Well, when we integrate these cross-frequency terms over an integer number of periods, they're going to wind up going away. So what we'll find is that in a multi-frequency circuit, so let's say for V of t is VDC plus V naught at omega 1 cosine omega 1t plus some phase angle. Let's just call it V1 plus V naught 2 cosine omega 2t plus some phase angle theta V2, and so on and so forth. Our effective value just comes out to be the square root of VDC squared plus V naught 1 over the square root of 2 squared plus V naught 2 over the square root of 2 squared, and we keep on going. Well, this could be expressed as simply V effective at DC, which is just the voltage itself, squared, plus V effective at omega 1 squared, plus V effective at omega 2 squared, and so on and so forth. So if we ever have a signal that has multi-frequency components, we can effectively just find the effective value of each of the frequency components, square them, add them together, and take the square root, and then we have an effective value for the signal as a whole. Why this might be important in the future. How many of you guys know what a Fourier transform is? So you guys haven't had Math 245 yet, for the most part? Okay, well, at some point in the very near future, you're going to have a class where you're going to learn that any periodic signal or actually any signal whatsoever, can be deconstructed into a bunch of separate frequencies. So a square wave can be made to look like an infinite sum of sinusoidal signals, a rectangular wave, triangular waves, all of that kind of stuff. Everything can be decomposed into a sum of sinusoids, which means with this equation, we can find the effective value for literally any possible periodic signal we would ever see. So pretty darn useful. All right, so that is enough out of me for today. When we come back on Monday, we will get into complex power relationships. We're going to spend 2 days on it because we're a day ahead. I desperately need you guys to ask questions and stuff like that, or we're not going to wind up spending 2 days on it. Okay, so tell me what it is that doesn't make sense so that I'm not just sitting up here in a monotone saying same exact shit I said in circuits 1. All right, you guys have a good weekend.